Okay, good. So let's do some mathematics. Yeah, so we're still in section 2.1. So we finished by talking about piecewise functions. And it gets really, I think we should have a pretty good idea on how they are defined and how to work them, right? If I throw in this example, f of x equals this thing, let's say 2x plus 1 if x is less than -2, 3 if x is greater than or equal to -2 but less than 1, and how about -2x plus 5 if x is greater than or equal to 1. Okay? A piecewise function. So again, I can ask you questions like, what is f of 0? And you would tell me 3. And how do we know that? F of 0 means x equals 0. That means it satisfies the middle inequality, right? That's where 0 is, in the middle. Where's my magic pen? So 0 is somewhere in here. So therefore, f of x equals 3 is our function, which is a constant, so it's just 3. Is that okay? Where is everybody? Today's the census day, they're all dropping. Right? Today's the last day to drop.
Yeah.
Yeah. No, I'm not suggesting anything. It's just a friendly reminder. But yeah, so, or if you need to add something. If I ask you what is f of 7, then you will go ahead and say, well, x equals 7. It satisfies the third inequality. So therefore, -2x plus 5 is our function. Right? What? What did you say? Did you say -9? That's what I heard. That's what you said. Because you're all shy all over something. So here we go. So do you remember that from Monday?
Yes.
Now, I can ask you, can you grab that thing? And that's where the fun begins. Can we grab this function? Because really, it is 3 separate functions, each one of them representing a line. And you all know how to graph a line, right? The first line, 2x plus 1, how do you graph it?
1 on the y-axis.
1 on the y-axis.
But up to over 1.
Yeah, up to over 1. Now, but if I just tell you, do we have to start on the y-axis? If I give you any other point on that line, can you start from that point and do a slope? Because to be on the y-axis, x has to be 0, and it's not part of the domain for this first portion of it. So I'm just gonna cheat a little bit. This is how I like doing this problems. So first of all, I'm going to focus on the points where the, -2 and 1, that's where the definition of a function changes, right? Before -2, I have one function, and after -2, I have another function. So before -2, I just have a straight line, 2x plus 1, okay?
Before it or on it?
Before it, right? So for all x values less than -2, so in this region, the graph would be 2x plus 1 of that function, right? Now this is not a graph, I'm just circling the region. So how do we graph 2x plus 1 on that region? So I'm just going to grab any point that belongs to that line on that region. Let's say, if I take x equals -3, where's the value of the function when x is -3? -5? Isn't it?
Yeah.
If you plug -3 in here, you'll get -5.
But
So
isn't it -2x plus 5, not plus? Is that what we use?
no. for the negative ones, before negative 2, it's 2x plus 1.
So yeah,
Oh, okay.
negative
Yeah.
5.
So negative 5, 1, 2, 3, 4, 5. So let's say here's a point. The slope is 2, right? Up 1 over 2, so here it is. Here's that line. So it goes over here in this region, and then it stops at x equals negative 2. Because at that point, when x equals negative 2, my function just changes to something else. Okay? So this is just the part of the graph when y equals 2x plus 1, when x is less than negative 2. So here's that region. To the left of that invisible line, x is less than negative 2, so your function is that. That's 2x plus 1.
Where'd the point come from?
I just made one up. I just took negative 3, plugged it in there.
Oh.
I just know it's, because I cannot do the y-intercept, because y-intercept passes that negative 2 frontier. Now, since it is strictly less than negative 2, since it's strictly less than negative 2, I'm going to leave an empty circle on that line to show that it kind of gets there, but not quite. Okay? So that's the first part. It's a straight line up to negative 2 on the x-axis. Now between negative 2 and 1, so here's 1, my function is constant, always 3. So I'm just going to do, 1, 2, 3. I'm just going to do a straight line. Goes from negative 2 to positive 1. Then I'm going to fill in. I'm going to fill in one dot and leave the other one empty because it's strictly less than 1. So it's another piece. And then from there on, my line becomes negative 2x plus 1. Okay? Now how do we sketch that line? We just need any point, and then we'll do the slope from there. Right? But see what happens if I just take 1. If I take this value of x, 1, and I plug it into my function, what do I get? 3. So it actually will start at this point. It will fill in that dot, and it will go down to over 1, like that. It just happened to connect. They don't have to connect, they just happen to connect here. They stay disconnected there. Right? If I take 1, plug it into my function, I'll get 3. So it
So
connects.
you just pick some random number to find out like where to put the point?
You can say that.
Okay.
You can totally say that. It's just,
number in the set.
yeah. So
In
the reason why I picked 1 for the third one, because 1 is part of the third set, right? So then it happened to give me 3, so they connected. For the one in the middle, it's easy, it's just constant, equals 3 all the time.
so that means no matter what it is, it's gonna be on just 3.
Yeah, so it's a constant, it's always 3. And the one before, I cannot pick negative 2, because it's strictly, I mean, I can pick negative 2. It will give me, what, negative 3? But I just have to leave it as a circle because it doesn't quite get there. And then, but it's easier to pick something from the left and then go up to over 1 to do the slope. Okay? That makes sense. It's kind of a messed up way of graphing things. Another thing you can do, you can just graph all 3 of them, period, and then erase parts that you don't need. That's another way of doing that. But you have to make sure that you erase parts. Otherwise, your graph won't pass the vertical line test. Check this out. If I just do that, if I just graph, here is y equals 3, so it's always that. Here's 2x plus 1, so it starts at 1. So they connect there, right? And here is, 4, 5. So they do that. These are all 3 lines at the same time. This is 2x plus 1, this is negative 2x plus 5, and this is y equals 3, right? And then you just have to erase parts that you don't need. So before negative 2, you only have this line right here, right? Before negative 2, that's the only thing that you have. So you're going to erase everything else. It's getting confusing.
Mm-hmm.
In the middle, you just keep the constant, so you erase that part, and you erase this part, and then you erase that part, and you erase that part. You're just erasing things that you don't need. And you get that graph. That's probably more confusing, I don't know.
No, that was
Isn't that filling?
Yeah, one of them is, which one? This one,
That
right?
graph.
Yeah. Yeah, so either way, graph all of them, but then start erasing parts that you don't need. Because if you don't erase, that whole big mass fails the vertical line test and is no longer a function.
Well, that fails the vertical line test anyway, doesn't it?
No, because see that it's an empty circle, that's a filled dot. So it'll actually, it hits the filled dot, but it misses the circle. And so, yeah, if I left it like that, then you would be right. It fails the vertical line test at that point. So this is what? What did I do?
Even though they're separate functions, it still fails the vertical line test. I thought it only had to be like one function that passes the vertical line test.
Well, the whole thing has to pass the vertical line test. This is one function. It's just one f. It's just defined in 3 pieces. And I have to be very careful that on the right I don't have any overlaps, and I don't. See, that's why on one end -2 is included, on the other end it's not. See, if I did include it on both ends, then it might, you know, fail the vertical line test. Fun stuff? All right. Well, when we're eventually going to learn how to, you know, we know a little bit about parabolas, but we'll get to know how to graph parabola in any point, how to do a cubic, square root, so we can make those functions more fun. We can have some curvature in addition to straight lines. Let me do this example. If I just do this, I don't know, 1, if x is less than 1, and then something like this, x squared minus 25 over x plus 5, if x is greater than or equal to 1. Let me share something. So one part is pretty simple. For everything less than 1, on the x-axis, so here's 1. So for everything less than 1, we just get a straight line, y equals 1, with an empty circle. Is that okay? For before 1. But after 1, it turns into this thing that we haven't really dealt with yet. Now, just by looking at that thing, can you tell me the domain of that expression? What is the domain of that?
X doesn't equal -5.
That's right. X cannot equal -5. Okay? Because otherwise you get 0 in the denominator. You agree with that?
Mm-hmm.
You also get 0 in the numerator, but we don't care. We don't want to get 0 in the denominator. So we know right away that x cannot equal to 5. Now, can I simplify that expression? Can x squared minus 25 over x plus 5, can that be simplified?
X minus 5.
Right. The numerator is the difference of 2 squares. Did I write 5 here? I meant -5, right?
Yeah.
Yeah, I want 5. Let me change this problem a bit. -5. So x cannot equal 5. Is that okay? Sorry about that.
Wait, so
I just changed it a little bit. My
X
denominator.
plus 5.
yeah.
Yeah, so then it's x plus 5. Sorry. Doesn't make it. Oh, because you're ahead of me. Okay, so if I reduce x minus 5, I'll get x plus 5, but x still cannot equal to 5. That part stays with that expression. Just because our function was originally defined as a fraction, that issue stays with us. X cannot equal to 5. Okay, so how do I graph that? It will start somewhere here, right? If I plug in 1, I'll get something like 6. And then it goes as a straight line. I need more room. And then it goes as a straight line with a slope 1, over 1, up 1.
Where did the 6 come from?
When you plug in 1, you get 6, right? X plus 5.
Okay.
But there's one little issue. In order for me to represent on my graph that x cannot equal to 5, I have to make a hole in my line. Okay, that's how you show that there is a one point where a function is undefined. Is that okay? What do you think of that? Okay, so but again, even we were able to remove that denominator, it did not affect the domain. The way the function was written originally, it created an issue at 5. And this is what you do if you just want to kind of poke a hole in your graph. You just put a term like that in the denominator.
So with the 1, it's on the y-axis, it's 1, and then on the x-axis it's also 1.
Right, because that's how we define
it. It doesn't go bigger.
Right. But if you go bigger than 1, it jumps to that other line.
No, with the x plus 5, how do you get that one?
Well, I simplified this expression, x squared minus
Yeah.
25, so I got x plus 5.
Yeah.
I just have to make sure to keep a hole in it, because of the denominator. That's 5, yeah. Here's another example of something similar. If I do this function, so let's say we have equals 5, if x equals 1, then it equals x squared minus 1 over x minus 1 if x does not equal to 1. Okay? So it's kind of the same idea. I will take x squared minus 1 over x minus 1, and I simplify that. It will reduce to x plus 1. Right? But again, x cannot equal to 1 because of the denominator, and that was actually kind of given the way this function was defined. X cannot equal to 1. So everywhere on this graph, what this means, everywhere the function is just x plus 1, except at one point. How do you graph x plus 1?
1.
Okay, start at 1.
Wait, doesn't x not equal? Oh wait, I'm not.
So that's going to be open.
Right, that's going to be open. At 1, I'll have an open circle.
Wouldn't it be negative 1?
No, positive 1.
And then you're going to just put a dot.
And then just put a dot, whatever I believe 5 is, right? So it jumps to 5. Because when x equals 1, the value of the function is 5. So it has one point just kind of hanging, and then it has a line below with a hole in it.
What would that ever represent?
Well, I don't know. You're making an experiment. You're collecting data, and everything is nice and pretty and linear. Okay, but then there's one point things kind of went haywire. All right. So at 1, just your data point has this jump. So everywhere else, it follows this pretty little line, but at x equals 1, whatever the x is, whatever 1 is, I don't know, things jumped to 5. And I don't know what you were doing. Could have been doing whatever you wanted in a lab, according to data. I don't know.
Making an algebra quiz.
Could be.
So did you just choose 1 on the y-axis just so the x did not equal 1?
No, I chose 1 on the y-axis because that's the y-intercept,
Oh, gotcha.
right? So that was, if I had x plus 2, it would be 2 on the y-axis. Okay? So that's that. Okay, let's try a little word problem. I wanted to do number 44. Or maybe 42 as well. Let's do 42. Oh, I don't have all the parts. It's got big. So what's the story? Can you read that? Is that too small? Remember your steps 1, 2, and 3. Right? Remember your steps 1, 2, and 3?
Mm-hmm.
What are they?
Read it, read it again, repeat steps 1 and 2.
Very good. Does the story make sense? So here's our little river, and then you're building something like that. X, X, X.
So he doesn't need a fence on the riverside?
Right, he doesn't need a fence on the riverside.
I was like, why is it not in the river? Oh, that was a good trick.
Yeah, well, right, that's what it says. A river forms one side of the corral, so you don't need a fence. And then we have this picture, you can kind of see that it's not.
Horses can swim.
And clearly cattle as well. But, all right, so we need to come up with a function for the area of both of them, right? I mean, we need the total area, right? So we're looking for the area, so total area.
Does just need to know the perimeter.
I know the perimeter. Well, not really. I don't know the perimeter. I know the total fencing used, right? Is that right?
Yeah.
If I just add up all the fence, I'll get 360, which does not equal to the perimeter. But in order to find the area, I mean, it's an area of this big rectangle. What do I need to know? In order to find the area of a rectangle, how do you find the area of a rectangle? What? Length times width, whatever you want to call them, right? Well, what is one side?
X.
Okay, so one side is x. So let's say, is that length or width? Width. So width equals x. How about the length? What is length equals to?
You know.
2x?
To it? Well,
Is
no,
it?
no.
And those are not squares.
Yeah.
Those are rectangles, right? Fence encloses 2 adjacent rectangular corrals. So they're not squares, right? But I do know if I add this side, that side, and all of that, I'll get 360, right?
So,
That's what this information is, 360 yards of fencing.
360 minus x cubed.
Well, minus 3x, because we're adding
Oh,
here,
yeah,
right?
minus 3x.
So that's right, L would be 360 minus 3x, right? Because this is x, 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 and the rest will give you 360 together. Does that make sense?
Then,
Is that okay?
so multiply that by x. Then?
Yeah. So then the area, length times width, so it's x times 360 minus 3x. Okay? So that's that. That's part A. Express area as a function of x. So if you give me the value for x, right away I can figure out what the area is. Is that okay? You can expand it if you want to. You don't have to. Negative 3x squared plus 360x. That is a quadratic. We're going to call it a quadratic function. We'll study quadratic functions in chapter 3 in greater details, how to graph them and so forth. But look at the question B. Find the domain of the function. Now, if I just wrote that function on the board, negative 3x squared plus 360x, without giving you the story before it, you would just say, well, domain is all real numbers. There's nothing to worry about. There are no square roots, there are no division, and so forth. But if you put this function into perspective of this particular problem, then what kind of values can x be? Can x be negative? No, that wouldn't make any sense. You cannot have a negative side. X cannot be 0 either, then you don't have anything, right? You just have a fence along the river if x equals 0. So you know that x has to be greater than 0, period. Right?
What does the domain mean in relevance to the
Well, again, what values can your variable be? That's what the domain is.
Okay.
Okay, so negative values here wouldn't make sense. 0 wouldn't make sense because you don't get yourself a fence. So the smallest, so x has to be bigger than 0. But what is the largest x can be, right? I cannot make my x, is it 360? If x is 360, look, see if I plug in 360 in for x, I'll get a big negative result as well.
360 minus 3x.
So basically kind of look at this. You just don't want to get 0. You don't want to get 0 in here, so x is greater than 0. And you don't want to get 0 in there. Well, what value of x gives you 0 in that parenthesis? 120, right? So x should be strictly less than 120.
Wait, what just happened? How did we figure out 120?
Well, because if I let my x to be bigger than 120, then I'll get a negative value in this parenthesis, right? And I'll end up with a negative area, and it's just going to be a whole, right? Because I mean, by definition, I do have to build 3 of these things, right? Out of 360 feet. So it should be less than 120 each, otherwise, right? If I let my x to be bigger than 120, then I don't get to build 3 equal parts. So for this specific problem, x has to be between these 2 values, otherwise you don't get it. Okay? Does that make sense?
Yes.
All right. Now, C, using a graphing calculator, graph the function, and blah, blah, blah. Now, pull your graphing calculators if you have one. If you don't, that's all right. Because I can graph this function. It will look like that. Between 0 and 120. If you have a graphing calculator, you plug that function in, and you let your x to be between 0 and 120, it will graph something like that. So the question is asking you, can you find...
Wouldn't they be open circles?
Yeah, it could be open, right?
Because they're not supposed to include.
Yeah, technically you're right. But the question is, so this is the graph that represents the area of this region. Now, can you pinpoint a point at which the area is the maximum? What is the highest point?
The top.
The top.
Yeah, that thing, right? This is the max. Now, parabolas are symmetric creatures, so I can just guesstimate that this value is 60 here. It's halfway in between. Because parabolas are very symmetric. Okay? So that actually tells me when x equals 60, it will produce the largest possible area. That makes sense?
Yeah.
Because, basically when you graph in calculator, if you move that little tracer to that point, you will see that x equals 60. Okay, so x equals 60 produces the largest area. And I can find that largest area by plugging in 60 into that function. A of 60 would equal to 60 times 360 minus 3 times 60. Right? That's what my function is.
Wait, why is it parabola rather than just like a straight?
I just know too much, but this is if your calculator, it will give you that graph. But then later we'll know that everything that has a square, all quadratic functions will be parabolas. Because right, this problem was asking you to use the graphing calculator, because we technically don't have that knowledge yet. I just don't have one on me. So whatever that is, so this is 60 times 180. Man. What's that?
10,800.
Yeah, 10,800. 800. Are we in feet? Yards. We're in yards. 10,800 yards squared. So that's the area. Okay? But we'll be doing those types of problems later in chapter 3, given a story, come up with a function, and then we'll be able to find that point that's called the vertex without graphing it or anything like that. There are ways to predict what the vertex is. So we're able to figure out how to divide our fencing to build the largest possible area. Did that make sense? Kind of?
Does that mean that on the graph when x equals 60, y equals 10,800?
Yeah. So this point right there is 10,800, and that will be the largest that function
Where did
reaches.
10,800 come from? Is
Well, we'll just
All
conclude
right,
that.
okay.
So there is an economist, a physicist, and a mathematician trying to solve this problem. Because the farmer asked them, I have 360 yards of fencing, I want to have as many animals as possible, blah, blah, right? So the physicist sits down and does all this wonderful work and comes out with an answer. Well, you got to do this. 60 yards, blah, blah, blah. They'll enclose the largest area. Therefore, you're going to end up with the most counts. Okay? I'm telling you a joke, by the way. And if you laugh, you should just switch your major to mathematics after that. It's a very dry joke. Well, an economist is like, well, who cares? Why do we need to spend resources on all this crap? Well, just build whatever you want. Build any shape. Shove as many cows. One on top of another, who cares? Well, a mathematician grabs just few little pieces of fencing, builds a little fence around himself, and goes, well, I'm outside. All right, so no math.
I don't get it.
Well, basically the message is that mathematician gave the best and the most useless solution. So everything else is the fence for the cow. Well, he is the only little person standing outside the fence, right? So the rest of the planet, that's where the cows
That
live.
wasn't that funny.
It's hilarious. That is hilarious. A true story. If you tell this joke in the class, that's called complex analysis, you get an automatic A for the semester. Yep, that's that kind of level of humor here. You ace classes just for one joke. True story.
We get an A if we tell you a math joke?
If you make me laugh,
Oh, okay.
then you might. Anyways, good. That's a good joke. One day you might get it. All right, good. So let's do another one at least.
Did you just make that up?
No, this is that joke requires
Critical thinking.
not just critical thinking. It requires I mean, you can like defend a PhD thesis based on that joke.
It sounds like you just made it up.
No, I'm not that smart. I cannot make stuff like that up. I'm not making this up. People, there are branches of mathematics devoted to that joke.
Oh my
That's sad.
Well, yeah,
gosh.
here's another one. I'll see what the 6 o'clock class is. I usually get one person to laugh in college algebra at those jokes, and then we'll have a conversation after class, and we'll get them to switch majors. And if I don't want to laugh, there are no laughs. Come on, this is a funny joke.
So
All right, so from a 12 by 12 centimeter piece of cardboard, you cut out little squares, you build a box. Does that make sense? So you have this thing, 12 by 12, you're going to cut out little pieces, call them XX. Fold it, you got yourself a box. All right, that's what this thing represents.
So each X is 12.
Now, each side originally was 12,
Oh, okay.
right? So you take from a 12 by 12 piece of cardboard, you cut out square corners, and the dimensions of each square corner is x by x. So we do that, x by x, x by x, and then you fold the thing and you get yourself a box, okay? Now can you come up with the volume of the box as a function of x? So we're looking for v of x. So we're going to up with the box. Now, how do you find the volume of a box?
Times width times height.
Yeah, right. So it's length times width times height. What is the height of that box? X, right? Because that's the size of those squares. Now, what about the length of one side?
12 minus x.
Well, 12
Oh,
minus
minus
2x, right? So it's 12 minus 2x, and then it is 12 minus 2x.
So the height is X.
Right. That's you have a little picture there. So then the volume would be x times 12 minus 2x. Right?
we don't put that. So
But
we don't like distribute that other x. No.
well, the auto operation suggests you should square it first, right?
But are you going to?
I can if you want me to.
Does that make it more difficult?
No, but I would like to see whether you remember how to square a difference. That came up a few times. How do we square 12 minus 2x?
Remember?
You square the first,
No, obviously
144, then minus. Not yet.
Or
Oh, I'm sorry. Yeah.
How do you square difference?
In there. So
You
minus
multiply this two, what do you get?
4x.
24,
24, double that.
48.
48x. Oh, I'm not going to answer that question. This is your homework. Can you
Spoiling.
figure out where that came from? Again, I'm using the formula that I've shown you a few times already. And this is the formula that you really need to know. So when you're squaring a sum or difference, there's always a double product in the middle. So then if you distribute the x, now you'll get 4x cubed minus 48x squared plus 144x. So this is what it looks like if you expand it.
You don't have to.
No, you don't have to. Actually,
Computer
it's
say you have to.
it might if it asks you, then. But if you ask, you should definitely be able to square a binomial because they'll show up in other places. But this form gives me a whole lot more information that I need. So find the domain. So that's the same as before. X cannot be negative, would make sense. X cannot be 0, then you don't have a box. You just have a piece of paper. So what is so x is strictly positive, right? So x could either be 0, a little bit positive, or what is the largest value x can be? This is 12, and you're cutting from both ends. 6. So x is strictly between 0 and 6.
Wait, where did the 6 come from?
But it couldn't be 6 because then you couldn't fold it.
Right, so that's why I'm making it strictly less than 6. But 6 would be the whole thing is 12, right? Well, you're cutting from both ends. So it can be, the largest it can be probably 6. It's going to meet in the middle. But not exactly 6, because then again, you just cut 4 squares, and you don't have anything left, right? Now to graph this, that's where you really need to use a graphing calculator. Will get a little bit trickier to graph. Okay?
Wasn't it just something that's not-
No, it's a cubic, so it's a little more complex.
Was
Okay.
that one of the
Yeah, isn't that the one that like goes like that?
Well, it will. I mean, if we were to graph this, it will. There's a 6 here, so it will probably be like that.
Yeah.
That will be the graph. But it goes through the origin. But we only need this part. Okay? Because that's the domain from 0 to 6. So somewhere here is the maximum. Now, it doesn't have to be 3. In this case, the whole symmetry thing I was telling you about parabolas doesn't have to be the case. So I can just go ahead and say x equals 3.
It's not a parabola. So
Right, it's not a parabola, so it doesn't have the 3D symmetry. So in this case, you really have to plug it in a calculator and locate that point. So since we don't have that on us right now, we're going to probably stop. How many times 12 goes into 96? Oh, that's bad. 8, right?
Yes.
Never mind.
Yeah, it's 8.
Yeah. Oh yeah, sorry. I don't know why I'm calling it. X squared minus 8. So yeah, at this point, if you had your graphing calculator, that will come out to be actually it'll come out to be 2.
If we had it on a graphing calculator, what are we looking for?
Well, you'll be looking at the graph. You'll first graph this thing,
Yeah.
and then you would just use the trace. You see the trace button?
But how do you know where the exact maximum is? Does it tell you?
Yeah, it'll tell you. Can I?
So if I go to the table and it's like 2, and then the highest point is like 128, is that?
Yeah, it could be. But that would be, if you go to the graph, so let me show you. And I don't know. So here's our function. 4x cubed minus, what?
I type it in right?
Yeah.
Yeah, that looks right. Now, the important thing is your window, okay? Because right now, your x from negative 40 to 40, and that's over, you don't need that much. We just said from 0 to 6, so let's do it from 0 to 6, okay? On the y values, again, you don't need to go from negative 40. You can go from 0 to whatever. So let's do, I don't know, 200 maybe, okay? So now if I do graph, you see I'm hitting the graph button. So it'll give me this graph. All right. Well, now you can use the trace button. If you do the trace, See if I start, see that little thing that travels along the line? You go left and right, so I can just go here, so it looks like, you see, getting closer, 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 closer. Looks like somewhere around 2 is that maximum point, right?
So doesn't you just gotta like guess that?
Yeah, so at least you kind of guesstimate. It looks like it's 2. So then you can go to that, where's the table? Yeah, see that
Second.
second table?
Yeah.
What was that?
No, second
Do the
graph.
table set.
Oh, second graph, sorry. Now how do you go back?
Just
I
do
don't know.
second mode.
Second, oh good. Oh, let's go back to graph. Second graph, here we go. So you see, here we go. When x equals 2, it's 128. So that's that.
How do you do that? There was a test, a question on the quiz about the ask mode in table, and I didn't know how to do it. Can you show us something?
I just did.
That's what you're doing?
Yeah.
Where's the ask mode? That's ask?
That's what?
That's ask? Like when you were in there? It said like use the ask mode, ASK.
Oh, I don't know what that is.
Yeah, I got that one wrong too.
I just did them all by hand, and I don't think I got them right.
If you get stuck on those tech issues with your calculator, just go to YouTube. They have a zillion little people punching stuff on their graphing calculators, and they're all the same. So just go on YouTube, go
Little
TI-83.
people doing it?
Yeah, they're just the people trying to make, little money off of that. Now what happens? Okay, good. You want to do a break or you want to keep going?
Should we get out earlier if we
Yeah.
can?
Let's keep going.
Yeah, let's keep going.
Yeah, let's keep, okay, I like that. Section 2.2. Algebra of functions. So we can add, subtract, multiply, divide functions. Just like with any two numbers, you can do those 4 operations. Now with functions, there's going to be one more operation that we can do, and we'll study that in the next section in 2.3. But for now, this is just these 4 operations. And they do exactly what you think they would do. You can take 2 functions, you add them, you're just combining like terms. You can take 2 functions, you subtract them, you're combining like terms. You can take 2 functions, you can multiply them, so you maybe do some foiling, I don't know. And you can take 2 functions and you can divide them. So you might do some reductions as well, all right? So that's pretty silly. So basically the definitions, let f be a function with domain, let's call it A, and let G be a function with domain B. So A makes F work, B makes G work. All right, so those are the domains. So first, we can define the sum of 2 functions. Here's the notation. The new function is F plus G of X. Because again, remember, we can give our function any name that we like. It doesn't have to be just one letter. So this name represents, F plus G, sum of 2 functions, which literally means F of X plus G of X. So that's what this notation stands for, just sum of 2 functions. Okay? And that does exactly what you expect it to do. Just take 2 functions, puts a plus in between them. But what is the domain of this new function? And this is the more interesting question. So let's think about this for a second. What is the domain of F? No,
A.
right? Domain of F is A, right? So everything in A makes F click very well. What is the domain of G? B. Now I'm adding the two, so I want both of them to work at the same time. So I need everything that makes F work, and at the same time, and that's the hint, I need everything that makes B work. So I have two sets. I need to find everything that's in set A and in set B.
An intercept?
Intersection, very good. So I need to intersect the two sets. So the domain is A intersection. So everything that they both share. So both functions work at the same time. Very good. So that's the whole end, right away you think intersection. I like that you remember. So now the rest is kind of the same. You can do F minus G. So that's F of X minus G of X. Domain is the same, intersection of the two sets. We can do the product, F G of X, which literally means F of X times G of X. Again, the domain, I want both of them to work.
Wait, so if it's A and B, then it includes everything in A, everything that intersects in all B. I'm sorry, that
So
was
it's,
probably a
every,
dumb question.
so it's everything that
But-
both have in common.
But it's not the outsides.
Right, not the outside. Because
Oh,
again,
okay.
because
That's
A
fine.
might have numbers that are not in B. So that means there are numbers that might
So
G
it has to
go
work in
crazy.
A and B,
Yeah,
not
so that
A
may,
or B.
right. So that's why we do the intersection. Because we want both functions to function at the same time. So that's why we do the intersection. Now with the division, F over G of X.
That's what that's called, intersection.
Yeah, that little upside down thing. Yeah. We talked about that. Were you here that day?
Yeah, but I don't think we named it.
Sure we did. No, I can pull up,
Oh, okay,
everything
yeah.
is on record. We can totally look it up.
Wait.
So now here we have to be a little more careful. We still want both functions to work at the same time, right? So we still need the intersection. But there is one more thing that we need to avoid, and that's getting 0 in the denominator. So everything that's intersection, and also make sure that G of X is not 0. Okay? Because, we cannot divide by 0.
And if the numerator is 0, the answer is just 0. Right?
Yeah, if the numerator is 0, you get answer 0, which is a real number, and that's all good and dandy. Okay? Is that all right? Good. Well, let's do an example. F of X equals X squared minus 4, and G of X equals X squared plus square root of X minus 4. All right. So let's very quickly state the domain of F. What is the domain of F? So what is our set A? Just the way it's written.
All numbers?
Yeah, all numbers. Because again, when you look at something like that, there is no division, there is no square roots, all real numbers. Because we don't have any stories about cows. This is just a function. So all real numbers. What is the domain of B? That one has a square root, so we have to be a little careful. Remember how we do domains?
Negative.
Right, so x minus 1 has to be non-negative. So x minus 1 is greater than or equal to 0. So x is greater than or equal to 1. So as long as x is greater than or equal to 1, we're going to end up with a functioning function. If that makes sense. That's what the domain is. Yeah? So what is the intersection of the two? What is A intersecting B? What do you think? What do they have in common? All real numbers, and then all real numbers greater
Would
than
it
or
just
equal to
be
1.
greater than? Why would it be equal to?
Because you can get 0 on the square root. Right? Square root of
Alright,
0 is
okay.
0.
A intersection B is just the domain of B.
That's right. So since A is all real numbers, the intersection will just be everything greater than or equal to 1. So the intersection is this. So for everything that we're going to do, that will be the domain for the sum, difference, and so forth. So we'll keep that in mind.
That's just because A is already all real numbers, right?
Yeah.
So, if it was
So A is all real numbers, and that just kind of
Yeah.
to the right of 1. So that's what the overlap. Right? If I graph both of them, here's A, all real numbers,
Yeah.
and here's 1, including 1. So literally, that's what they intersect
Okay.
from 1 to infinity.
Why you included 1? Because then it would be 0.
But I can do square root of 0. Square root of 0 is 0.
Oh, you can?
Right. I cannot do 0 in the denominator, but I can do square root of 0. So let's find f plus g of x. So that's just taking f, x squared minus 4, adding g to it, and g was x squared plus square root of x minus 1. Am I remembering that correctly? So this is f, and this is g. So we'll get 2x squared plus square root of x minus 1 minus 4 as our function. Okay. Domain of this function would be all real numbers greater than or equal to 1. I don't even have to look at it because I know that from before. We did all the hard work before finding the domain. Questions on that? Is that straightforward? Yeah, so you do the same thing with the minus. With the product, I'll just have to do this ugly long FOIL. I don't think I want to. Do I want to? No, so let's just start dividing right now. Let's just do I'll read it real quick. So it's x squared minus 4 times x squared plus that. You know what? Don't FOIL. That's the function. I don't care what it equals to. We don't like foiling. That's the answer. That's the product. What is the domain of that function?
All real numbers greater than 1.
Or equal to.
Or
All right, good. All right. Let's do the divisions. Those are a little more fun. How about f of g of x? I'm sorry, f over g. So that's x squared minus 4 over x squared plus the square root of x minus 1. So I know it's still from 1 to infinity, including 1. I just have to make sure that I don't get 0 in the denominator. Right? That's the only thing I need to double check. But look, x squared, can x squared ever be negative? No. How about square root? Can square root be negative? No. So I have one thing that's never negative, another thing that's never negative, and I'm adding them.
So they can be negative.
So they can be negative. Right?
What?
But can they be 0? That's the whole thing.
Yeah.
So what will that give me?
0. In the
Well, if I plug in
denominator.
0,
Wait,
0, I
neither-
get square root of
If
negative
neither
1.
one of them can ever be negative, then how can it result in a negative?
But that's what I'm saying. So the result cannot be negative.
Okay.
But think about this. X starts at 1, right? So x squared is always positive, right? We already have that restriction from 1 to infinity. So x squared is always positive, right?
Where did we get the restriction? from the
That's what
first
we
two?
talked about 10 minutes ago over here. That's when we
Yeah,
did the
but-
intersection. What?
I just, I know.
That's what we did
Okay.
here. So we know that because of that. Because all of them will have that intersection for the domain. So that's why we did the intersection first. So we know x starts at 1. So if x is 1, you'll get 0 here and a 1 there. So that's always positive, right? Plus a positive, so that can never be 0. So then we're done. Domain is from 1 to infinity. Just we don't have to worry about anything.
So that just worked out that way.
Yeah, it just worked out. It happened to work out. We got lucky. If I flip them though, if I write this as g over f of x, I'll get x squared plus the square root of x minus 1 over that. Right, so I just,
Not x squared. Oh yeah.
am I going to get any trouble?
No, it'd be all real and then.
Can't be 2.
Can be 2. What else?
Oh.
What else makes that denominator
Negative
0?
2?
Negative 2. So it looks like we have, and it's always a good idea to factor your denominators. So right away you see 2 and negative 2 would be a problem, right? But now remember, we already have that restriction from 1 to infinity. That's where we're starting. That's the intersection of the two domains from 1 to infinity. So from 1 to infinity already excludes negative 2, right? Negative 2 is already out of that set. But positive 2 is there, right? So I have to remove positive 2 from the set from 1 to infinity.
And 1.
No, 1 is okay.
1 would make it negative 3.
Where?
1 squared minus 1.
But it's okay to have a negative in the
It just
denominator,
can't be 0.
right? I just want to make sure I don't get negatives under the square root. But I can get negative, positive in the denominator, just cannot be 0. So I have to make sure 2 and negative 2 are excluded. Negative 2 is already excluded from my domain. I just need to exclude 2. And that's how we do that. You just punch a hole where 2 was. So it's from positive 1, including positive 1, all the way to 2, not including 2, and then from 2 to infinity. Right? Does that make sense?
So why is it or and not and for the domain? Why is it?
Well, because again, I already did that. That's given to me, right? So I have this set from 1 to infinity, right? Now the other set, everything but 2 and negative 2. So here's negative 2, and here's positive 2. Everything else works. Right? So they overlap from here to here, and then from there to infinity.
Oh, okay.
But I need both of them. So that's why I'm taking the union of them. But yeah, I did find the intersection. It's just the intersection happened to be a union of two other sets. Okay? So remember, when you do the intersection in the very first step, that domain is going to stick with you for all the problems. Every time you do product, sum, difference, it's going to be that same intersection that we found at the very beginning, right? Only when you start dividing, you have to add an extra caution there where you just...
So it's not 0.
Yeah, so the denominator is not 0. Because again, with this case, 2 was perfectly fine for every other problem. But now 2 makes 0 in the denominator, so you have to exclude. Good? Okay. Good? Good. Good. Now, very interesting concept. And it will cause us a little bit of a headache. Difference quotient. Okay. So let me talk a little bit. You don't have to write this down. Let's say I have a function f. Okay, and I have a starting point somewhere here, so some x value. Okay, so if x value is x, what is the y value? Given that this is f.
X squared.
No, you're just making stuff up. I don't know what the function is. Function is f, so it's f of x, right? You just take this, plug it in there. All right, trick question. But let's say I want to move a little bit over to the right. And I'm going to call this distance that I moved over to the right, I'm going to label it with the letter h. Just because I can label things any way I like, I just chose to label it with h. So if this is x, and it's h extra units, what is this new point?
X plus h.
X plus h, very good. So then, what is the value over here on the y-axis?
F of x plus
F of x plus h, very good. Right? That's how the function notation works. Now, for whatever reasons that I'm probably not going to tell you about yet, I'm going to connect these 2 points with a line. Right? Can I do that? Sure. So we know 2 points on that line, right? It's x, f of x, x plus h, f of x plus h. Can we find the slope of that line? Can we express the slope in terms of this
Yeah.
change in y? You want to know why?
Why not?
Well, I don't know yet. You didn't laugh at my joke, so I'm hurt. What is the change in y? Well,
x minus
X, f of x plus h minus.
yeah, f of x plus h
Minus f of
minus f of x. Well, what is change in x?
f of x. F
H.
of x plus h.
Yeah, h, right?
Oh.
It's x plus h minus x gives you h. Right? So this expression really gives me the slope of that line. And the name of that expression is difference quotient. Because, well, there is a difference and there is a quotient. So we call our things the way we see them.
But so then why is it just the slope?
It is the slope.
What is
The
this?
slope is the difference quotient.
Yeah.
The same thing?
Kind of.
Okay.
Slope has a little more other meanings, but this is, I just built that by finding the slope of that line. Okay? So all you really need to get from this story is given function f, the difference quotient of f is f of x plus h minus f of x all over.
And when do we use that? Like, is this going to be different every time? Or
No, if you ask to compute the difference quotient of a function, then you know they're talking about that. And I'll do examples. So, if I give you a function, now let's do something simple. Let's say f of x equals 3x minus 4. Okay? And I ask you find the difference quotient. Which is, again, which is this expression. So let's try and set this up. If f of x is 3x minus 4, because there are 3 parts, right? It's f of x plus h, f of x, and h. So how do you find f of x plus h, given that f of x is 3x
what's
minus
h?
What's h?
4? H is h.
So,
So we don't know.
The amount of units moved over.
No, you're thinking too much. How does the function notation work? Because I've asked you that
3x
question.
Plug in
Minus
x plus
4
h
plus
into where x is.
Yeah, so that's all I wanted to hear. This is f of x plus h. right? Don't think about what h is yet. I'll see you in a year, and then we'll talk about it. Okay? We're not there yet, but it's important that we can at least set this up in a certain way. So that's f of x plus h. So let's just put it here. So f of x plus h is this. So that's what the formula tells me. First, write f of x plus h. Then the formula tells me subtract the original function. Well, what is the original function?
3x minus.
Yeah, so I'm going to do minus, and I'm going to put 3x minus 4 in the parentheses because I want to subtract that entire function. If I don't put parentheses, that means I'm subtracting part of it, but not the whole function. So put parentheses around your original function. That's f of x. And everything over h. So this is the setup. You have three parts, f of x plus h minus the original function divided by little lonely h. Now I'm going to simplify this. Okay? The way we simplify this, the rest is simple. You open up the parentheses. And you combine like terms. So you distribute the 3, you distribute the minus. Can I cross few things out? What can I cross out?
Everything except for 3x.
So 3x
Or
minus 3x.
3h.
What else can I? So yeah, everything but 3h. So 4 is canceled. So we're left with 3h over h.
And then do you cross the h's out?
Sure. Now cross the h's out. And you get,
3. And that's the
That's
difference.
that's the difference quotient of that function.
Okay.
Okay? But this is a very simple example. I can make my functions a little more, with a little more parts on it.
Okay, so what is the difference function? Does that-
You want me to talk about this? All right, let's talk about this.
Okay, sorry.
That's very disrespectful, whoever's making those noises. All right, so let's do that. All right, let's say we live here, our Steamboat Springs, right? And we're gonna go on a road trip. Wait, where are we going? Denver, all right, we're gonna get.
Zealand.
Right?
No, I just want to do it in one. How far away is Denver?
Like 3.5 hours.
In terms of distance?
Just 2 miles.
180, just to make math easier. All right. So this is our distance. Here we have distance, and here we have time. Now, how long did it take us to get to Denver?
2 hours. 3 hours.
So you're going 90 miles an hour?
Yes.
2 hours.
So 106.
You want to do 3 hours, then you go 16?
No, I was gonna say 160 to make math easier.
No, math would be easier if you do 3, then 160 works, or 180.
Oh yeah. No.
Right? So let me ask you, what is the average speed of your trip to Denver?
60 miles.
60 miles per hour. How did you find that?
180 divided by 3.
Or total distance traveled divided by total time, right?
Yeah.
Okay, good. Now what if I ask you, find the slope of this line?
3 of 180 over
3. Will still be 180 divided by 3, 60. So remember when I asked you, I think it was you who said that, what is the slope when you said rate of change? So the slope is the rate of change. So if our function is the distance from, on our trip, then the slope, because we didn't go like that. We didn't drive 60 miles an hour all the time, right?
Yeah.
Our speed was fluctuating. So we were probably going kind of slow at first, and then maybe going faster, and then, I don't know, not going anywhere, and then got to Denver. This is our function. We might have gotten lost somewhere. And I didn't try very hard to avoid the vertical line test here. It passes the vertical line test. Here it looks like I went back in time a little bit, but it didn't happen. So you see, like here you're kind of going slowly, right? It takes you more time to cover shorter distance, while here you're going really, really fast, right? It takes a very small amount of time to cover really big distance. Like here you're probably not moving, so that's a speeding ticket. I don't know. So you're going way too fast over here, right? But on average, you went 180 over 3. Okay, good. But let's say here's the point where you got the speeding ticket, right? So, you know, you were going 100 miles an hour at that point. How can they tell? When they say 100 miles an hour, that means you were going 100 miles an hour at that very instant when they, you know, did the radar thing over there, right? So now we're not talking about the average speed, we're talking about how fast you were going at an instant, right? And the way we do that, we kind of start doing a little lines at that point, is we're trying to compute the slope of the lines over a very, very small time interval. If I can find your average speed between now and 1/10 of a second from now, I have a pretty good idea how fast you were going at an instant. So that's what h is. H is the interval in time over which I'm finding your average speed. Okay? So really, like that radar gun, it's not, you know, they send like 2 signals, very small interval, and get 2 replies, so they know how far you traveled, you know, in like 1/10 of a second. So they know on average, on that 1/10 of a second, you were going 100 miles an hour. So yeah, you were speeding on average, right? Because if you see average speed of 60 miles an hour, I have no idea whether you were speeding or not over 3 hours. But if your average speed is 100 miles an hour over like 1/10 of a second, then you were speeding. So that's what they do. They make that little interval, the time interval, get very, very, very small. Okay? So really what they're doing, they're putting a line to the graph at one point. That's what they do. And that one point is that your little h. Basically, you shrink the h, and then you're finding a precise, more precise average speed. Okay? So really, in those all expressions, this little h is virtually 0. Okay?
And that's why it cancels.
And that's why we want to cancel it. Because and again, you'll be doing this, like all this analysis of h equals 0, not in this class. In this class, we're just training you, can you set this up and cancel that h? That's really the goal. To cancel this h, because that h will eventually shrink to 0. Okay? And that's how we do the speed, like on a helicopter. You know how they do the speed on a helicopter? Because think about this, they're moving, so they cannot do the radar thing, because you know, the radar, it bounces off your car, but they're moving, so like, you know, like the guy in the bushes with the gun, then yeah, he's fixed. But with the helicopter's moving, so there's literally a guy with a stopwatch, you know, and you driving on the highway, and sometimes you're passing like a white line, like in the middle of the highway, and like 100 feet down the road, there's another one. So that he goes click, click. How long it took you to go from one line to the other line, so they compute the average speed over 1 second. So that's pretty close to how fast you were going at some, right? What? That's what's going on. That's really an idea. But for the linear function, it came out to be 3. So all we have to get from all these stories is what the difference quotient is, that's that expression, how to set it up, and what it means to simplify that. So that's that little h goes away. All right, let's do another function.
So are we gonna get any kind of like study guides for the test with the formulas we should know? Or
Yeah. So here's a function. And again, I want to find the difference quotient. So that's the general expression. So again, 3 parts. First part is f of x plus h. So we're going to take x plus h and replace each x in our original expression. So we'll get x plus h squared plus 2 times x plus h minus 3. So this right here is f of x plus h. So all I did, I replaced each x with x plus h. Is that okay? Minus the original function. So I'm going to put that one in the parentheses. X squared plus 2x minus 3 all over h. So that second part is f of x. And I'm going to simplify that till that little h in the denominator cancels. Sometimes there'll be problems with the new h appears in the denominator, and that's going to be all right, as long as the original one goes away. So, how do you square x plus h?
X plus h, x minus.
Plus 2h.
Oh, yeah.
Yeah. What?
Square xh.
X squared plus 2xh plus h squared. That's right. When in doubt, FOIL. X plus h times x plus h. Distribute the 2 plus 2x plus 2h minus 3. And then distribute the negative. Minus x squared minus 2x plus 3. All over h. What can I cross out?
X squared,
X squared
3,
and 3,
and 2x.
2x. Good. Now, you see that every term that is left in the numerator has at least one h in it. So I can factor an h out of the numerator. If I factor an h out, we're left with 2x plus h plus 2. Cancel the h's and we're done. The second you cancel that h, we're done. So this can tell me how fast you were going at almost any instant in time. Where x would be the time, h is irrelevant. H is very, very small. Okay? So if you have a function of your position, you can always find the speed, how fast you were going at any given point. Also, you can go the other way around. Having the speed, you can always go find the position. And that's how they started that many, many years ago. They looked at the stars, how they move, and they would predict the position. And all of a sudden, the Industrial Revolution came out of that. And the fact that you can go buy a new iPhone goes back. This is the reason for us being technologically advanced, believe it or not. The fact that we can just drop that age. Like that. Seriously, this is the spark of the Industrial Revolution right there. I'm not making this up. The fact that we connect distance to velocity, how fast we're going, and we can totally think of this an abstract notion, you know, internal combustion engine was the next thing they came up with. Yeah, true start. All right, now let's have a little more fun. 1 over x, things get a little fuzzy. Okay, I want to do difference quotient with that one. So, this is the reciprocal function. All it does, it takes reciprocals of things. So if I'm asking what is f of x plus h, I'm just asking what is the reciprocal of x plus h, and that's 1 over x plus h. So that's the f of x plus h, given that 1 over x is our function. Minus the original function all over h.
Why did you do the reciprocal?
Well, because that's what I decided. That's my function, right? It's 1 over x.
Somehow, you have to multiply it by.
Yeah, I'll multiply by something. On homework 0, you had those types of problems where you have to find the best way to deal with this problem is to find the little LCD, which is x times x plus h. Right? That would be the least common denominator. And just multiply top and the bottom by x times x plus h over x times x plus h. That's the technique we use to simplify this. So this is new, multiplied by 1. So now see what happens. The denominator is easy. We just multiply the denominator straight through. H times x plus h. There's nothing really going on. But in the numerator, when you take this expression, x times x plus h, and you multiply it by the first term, something will cancel. What is it? X plus h, and what is left? X. Do you remember this question from last semester?
Yeah, kind of.
We did it like 7 times. It was on the final 2. But you were given that setup. So x minus, you do the second product, what is going to cancel? X, and what is left? Keep it in the parentheses, because we have to still distribute the negative. Okay. Now remember, we are after this little h. We want to kill it. When it's gone, then we're good. And we're almost done. So it's x minus h over h x plus h.
This might be a dumb question, but since it was 1 over x and 1 over x plus h, like why is the 1 on the top going away?
Oh, it's not. I mean, I can write it 1 times x. It wouldn't make a
No,
difference.
I mean like, it's not 1 over x. Oh wait, no, that's exactly what we had just. Never mind, I confusion aside.
Are you sure?
Yeah, I'm good.
What can I cancel?
X's.
Yeah, I can cancel 2 x's. And we're left with negative h over h times x plus h. And now we can cross out the h's.
Then it still leaves negative 1 on top.
Yeah, so we just left with the 1 on top. Still a negative somewhere, so negative 1 over x times x plus h. And that's the answer. Now we got a new h in the denominator, but that h doesn't bother us. It's it can be 0, no problem. We're not going to get 0 in that number. I can start ignoring that h. What did I just do? I just hit a bunch of buttons.
It?
What?
Is that it?
No, I have one more.
Why didn't we take a break then? I haven't even done early.
Well, no, we still. I have you 10-minute breaks. I have you for another 6 minutes. Right, and we're done at 40 past the hour, not 50. We're good. We still have enough for this little fella. And that's always fun to deal with that guy. So again, we'll set this up. So if f of x is square root of x, then what is f of x plus h?
Root of x plus h.
That's right. Right? Minus square root of x over h. So again, this is f of x plus h. That is f of x.
Why does the h get squared?
But,
Why does the h get squared too?
well, because everything, that's the whole function. Function is the square root
Yeah, yeah.
of everything that you pile in it. So You know, the function is just big square root. Right?
Yep.
So it's up to square rooting things, and I'm asking you, what is the square root of x plus h? What's the square root of x plus h? Now, in order to simplify that, I have to use what we call a conjugate trick. And you have seen that trick when we rationalize expressions, when we want to get rid of square roots and stuff. Because we want to get rid of those square roots, basically, that's the idea. But I cannot just walk over and start squaring them, it'll just be illegal. So I can square them artificially by doing this. Because I can always multiply my fractions by 1, right? That's the whole idea. And this is what I'm choosing my 1 to be. I'm making it exactly the same as the numerator, only with a plus in between. See what I'm doing? It's the exact same thing as my numerator, only with a plus. And what I'm about to
So why
do...
can you do that if it's with a plus rather than a minus?
I'm sorry, what?
How can you change the sign?
Well, because I'm not sure I understand your question, but I can do whatever I want on this side. I'm just going with the opposite side of what was here. If this was a plus, I would go with the minus. And the reason why I want to do that, because I have this formula, the difference of squares formula. If I multiply two things that differ by a sign, I end up with two little squares. And these terms are called conjugates. The two terms that only differ by a sign in the middle. They'll come back. You'll see conjugates again. But this will now allow me to use the difference of squares formula because I'm multiplying two expressions that only differ by the sign in the middle. You see that? The only difference is the sign in the middle. So then, using the difference of squares formula, I'll end up with the square root of x plus h squared minus the square root of x squared. Because that's what the formula suggests will happen. That in the numerator. In the denominator, nothing fancy, just straight out product. Right? Why is it so nice that we got those squares on top of those square roots? Yeah. The squares will kill the square roots, leaves us with x plus h minus x over h times. Right? So now I can start crossing things out. What can I cross out? I can cross out the x's and then the h. Right, we're left with h over h times all that. So I can cross out the h. And now we're happy. So it's 1 over the square root of x plus h plus square root of x. See, I got another h in the denominator, but it's okay to ignore it. If that h is 0, I don't get 0 in the denominator.
I don't understand how that stuff you did in the green up there is similar to, is the same thing as 1. No, over
Well, because my numerator and the denominator are the same, so it's 1,
okay.
right? Every time you numerate denominator match, you just cancel the whole thing. So they're the same. And this is what I'm utilizing.
Mhm.
So you see, again, make sure that those two are different, that the signs are different. And then you just get those little squares. Good. I have another minute if you have questions. So you'll have some practice with that on that homework, I think 3, and that's kind of an important skill. And I will add an extra video of just difference function problems. I made one a few years ago, so